This is video 33 in the lecture on the design of reinforced concrete beams. This is a calculation example of shear reinforcement. We will handle a very simple case of a simply supported beam, and the beam is loaded with a uniform distributed load of 190 kilonewton per meter in ULS persistent. The tension reinforcement is 3 diameters 32 and the compression reinforcement 2 diameters 20. We will start with calculating the shear force and make a choice of the inclination angle of the concrete strut. We will use stirrups straight with an angle of 90 degrees, vertical stirrups. The effective depth is total depth minus the point of gravity of the tension reinforcement, minus the concrete cover, and minus the stirrup diameter. But that's the one we are looking for. So we have to estimate something, we have to put in something to start with, and we have to check it afterwards if this is all right. So usually we start with 8 or with 10 okay, we will now start with 8, so we have D of 636 millimeters. We know that if you take cotangent theta as large as possible, then that will result in a small number of stirrups. So we will take theta here, the smallest we can, which is 26.6 degrees, or cotangent theta is 2. And d cotangent theta is then 1272 millimeters. It means the shear force that we need for the design of the stirrups is at a distance d cotangent theta, so that's why we calculate d cotangent theta. The shear force as a function of a distance s from the whole system of the beam by simple statica gives us this equation. The length of the system is 4,500, the netto length, plus the 300 is 4.8 meters. And the maximum shear capacity of the concrete struts must then fulfill the VED max, which occurs at the face of the support, and it means S is then 0.15 because the support is 0.3 meters width. So the VED max at the face of the support is 428 kilonewton. So at all times the concrete strut must be able to take the 428 kilonewton. We know that VERD max, the maximum capacity of the concrete strut, is a function of the inclination of the concrete strut. So we have to choose this inclination. So what we will do is we will do just the reverse. We will calculate the minimum or the maximum we will calculate the inclination needed to take up the maximum shear force. The maximum shear force at the face of the support was 428 kilonewton. And from this equation, we derive theta, and theta is 14 degrees. But we know that the minimum value of theta is 26.6 because cotangent theta cannot be bigger than 2. So we know already now this is okay because we only need 14 degrees and we have 26 degrees. So the VRD max is okay. Now, for the first crack, if this is the beam, this is one support, this is somewhere along the beam. This is somewhere along the beam. Then we will see if this is the system. Here is S is 0. Then this is the diagram of shear force. We will see at the first crack, at d cotangent theta from the crack, we calculate VED. So S is 0.15. This plus d cotangent theta is 1.422 meters. And at this distance, we will calculate the shear force. It's 186 kilonewton. In the second crack, again, a distance d cotangent theta alongside the beam, and gives you VED minus 0.56. It means we already passed half of the span of the beam, so that's okay. Now we will calculate VRDC, the capacity to shear force of the concrete only. For this we need the rho L, and ASL. It's easy here because the tension reinforcement is put over the whole span, the total span of the beam. So it's 2,413 square millimeters divided by the width and the effective depth, and it gives me 0.01265 as a density of the reinforcement. The shape factor is, or dimension factor K is then 1.56. And now we can calculate VRDC. K1 sigma CP is 0. There is no netto compression external force to the beam. CRDC was 0.18 divided by 1.5. K we have calculated. Rho L we have calculated. So at the end we arrive at 120 kilonewton. So 120 kilonewton shear force can be taken by concrete only. But there is a minimum value. If we calculate this minimum value, we must multiply it by BWD, or by the area of the concrete. Then we see the minimum is 71. So now we take the maximum of the two, which is 120. So we check, is now the VED that we have calculated smaller than VRDC, yes or no? We see that for the first crack, shear reinforcement is needed because 186 is bigger than 120. So shear reinforcement is needed. For the second crack, you see easily that there is no shear reinforcement needed. Then we first calculate the minimum amount of stirrups that we need. There is always a minimum amount of stirrups that you have to place. And the minimum density of stirrups is 0.08 square root of FCK divided by FAWK. And it's 0.876 10 to the power minus 3. Now we have to convert this into stirrups. The density of stirrups is defined as the amount is defined as the cross sections of the stirrups divided by the spacing of stirrups, dividing by the width of the concrete section, and sinus alpha. Alpha is now 90 degrees, so that's 1. So it's ASW divided by SBW, or SB. Take care, there is a B coming in. Huh? Now, if we combine this, then you can see that ASW divided by S must be rho W BW sinus alpha. This is 1. This we calculated, so we have 0.263. So ASW over S, the minimum value of the shear reinforcement is 0.263. Just never try to separate the S from the ASW. That's important. Otherwise, you can make horrible mistakes. So always keep that together, ASW over S. As a reminder, ASW over S is, of course, the cross-section of one bar, of one rebar of the stirrups, multiplied by the number of legs of steer that there are in one stirrup divided by the distance cleared, divided by the center to center distance of the stirrups. The first assumption was, if you remember, that we took to calculate D, the first assumption was the diameter was 8, so we keep this assumption. Otherwise, we have to recalculate everything. So we keep to this assumption. So the diameter is 8 millimeter, but we have two elements which are unknown, which is S and phi. The maximum leg clearance, we know it's 0.75 times D. Cotangent alpha is 0. So it's 0.75 D, which is 470 millimeters. So the distance between two successive stirrups cannot exceed 477 millimeters. We take the reversed calculation. We calculate what is the minimum spacing for a diameter 8 with 2 legs, and we need a density rho W. We need a density. No, we need not a density, but we need a reinforcement ratio of 0.263. Then we see that the minimum spacing of a diameter 8 is the 382 millimeters, which is smaller than 477, so that's fine. And we have always, we must round it off downwards. So we will take diameter 8 every 380 millimeters, 2 legs for minimum reinforcement. The shear force capacity of the minimum reinforcement is then, that is the capacity of the shear force reinforcement ASW divided by S. So we fill in 380 because we've chosen 380, not 382, and it's 132 kilonewton. So the minimum reinforcement that we've placed can take up 132 kilonewton of shear reinforcement, of shear force. And this value, the minimum stirrups, they start at the position S. It is just the general formula for shear. We plug in 132 and we look for S, and it's from 1.7 meters. From that point onwards, you put minimum reinforcement. The needed shear reinforcement now, we calculate ASW over S, which is with this formula, and we see that it is 0.374 that we need. We use diameters 8, 2 legs, and if you use it at a distance of 265 millimeters, it's 0.379, so this is okay. And then we look for the additional tension in the reinforcement at the location of VED. The delta F is then VED divided by 2 and multiplied by cotangent theta, because cotangent alpha is 0, so it means it's 186 kilonewton. So the needed additional reinforcement is, we suppose it's yielding, is 428 square millimeters. But there is a limit to that. To 186, there's a limit to that. The limit must fulfill this equation. The MED max, the maximum bending moment in the midspan of the section, is the uniform distributed load times the span squared divided by 8 is 547 kilonewton meter. We take Z as 0.9 D, it's 0.572. The bending moment in function of the coordinate S, and then we take the bending moment at the point of where we are calculating the shear force, which was VED 186 at S equals 1.422. So that's, we put 1.422 in it, and we see that the bending moment at that location is 456 kilonewton meter. If we now put those numbers in this equation, then we see that the maximum value of the additional tension in the reinforcement is 159 kilonewton and not what the 186. So we use 159. The available reinforcement at the first crack was 3 diameters 32, so that's 2,413 square millimeters. The needed bending reinforcement at the first crack is the reinforcement needed to cover this bending moment. So, and this is 1897 square millimeters. The reinforcement for additional tension is the 159 divided by 435, it's 366 square millimeters. So it means that the total needed reinforcement is the 366 plus the 1897 is 2263, but we have available 2413, so this is okay. So the tensile reinforcement can take the additional tension that is generated by the shear force. Instead of calculating directly the additional tension in the tension reinforcement, we can also use a mathematical trick and shift the bending moment curve over a distance of 1.5 z cotangent theta, which means 0.572 meters in our case. So we calculate the bending moment at the position s equals 1.422 plus the shifting 0.572, and the bending moment is then 532 kilonewton meters. If we calculate the needed reinforcement, it's 2281 square millimeters. So now you can compare this what we had calculated previously. It was 2263, so it is close enough. So this is all the same, or you shift the bending moment curve, or you calculate the additional tension in the tension reinforcement. Now we have to make a little sketch or a drawing. This is the drawing of the concrete itself. It's straightforward, there's nothing to it. Just remember, you always have to put the environmental class, the concrete grade, the reinforcement quality, and the concrete cover on the drawing. We start, for instance, now with the first rebar or with the rebars at the tension zone. We have 3 rebars, we call it a number 1. We have 3 rebars and call it a number 1. Diameter is 32 and the shape is a U shape with this as dimension. 5020 comes from the 5100, the total length minus 2 times the cover. Concrete cover is 5020, and the bend up portion comes from the total height of the concrete, of total depth of the concrete section, it's 700, minus concrete cover, minus the stirrup, and then again minus concrete cover and stirrup, but also minus diameter 20, which is the compression reinforcement. Then we take the compression reinforcement, it's 2 diameters 20, we give it a number 2, it also has a U shape. We must take care that this U shape will fit into the other U shape of the bars number 1. So that's why we take here this dimension, it's 5200 minus 40 minus 40, but we subtract twice the diameter of the bottom reinforcement number 1, which is outside. Then we come to bar number 3. Bar number 3 is just a technological reinforcement, because otherwise the distance between the compression and the tension reinforcement is too big. We have 2 diameters 8. We take the smallest diameter, which is 8, also in a U shape. This time for the length you must take care what do you decide? Are you going to put this rebar 3 outside? No, because the other bars are already at the outside, so you must put it inside. It means you have 5100 total length minus concrete cover left, concrete cover right, minus bar number 1 minus bar number 2, left and right, and you have 4,916. Then we have the stirrups. We have two zones. The zone with the minimum stirrup, remember it was starting from S equals 1555 plus 150, because S starts from the system, S starts from the middle of the support. So from the face of the support, it's 1555. So this stirrup, we call it 4A, was 8 times 8 bar, diameter 8 with a spacing of 380 millimeters. That was the minimum reinforcement. And this are the dimensions. How do we calculate the number? It's easy. It is this area. It's 1,390 divided by the center to center distance plus 1, and we have 4.6, and we make it 5. So we take 5 diameters 8 every 380. And for the dimensions, it's the total depth minus twice the concrete cover, it's 620. The others, it's the same thing, but for 4B, we have as stirrup reinforcement, we have diameters 8 every 265 that we have calculated. So we do the same exercise. And then this is a total drawing where we end. You have the compression, the tension reinforcement, compression reinforcement, technological reinforcement. You try to make this distance always smaller than 300 millimeters. You have the bending schedule, and at the end you can make a summary of it, which is where you calculate the total weight of concrete and the total volume, the total weight of steel, used steel, and the total weight of concrete. And then you have the steel usage, which is 151 kilogram per meter cube of concrete. It's just the total amount of reinforcement divided by the volume of the concrete. You can now calculate the needed shear reinforcement of a beam. See you next lecture.